In this tutorial, we're going to cover structuring a simple agent class combined with our OpenCV method. So this is going to allow our agent to run relative to certain steering criteria of an image's pixel data. This method is going to be incredibly useful. However, we won't go into the full depths of its potential extensions. So this is just a kind of general introduction to this type of methodology, but I highly recommend everyone spend some time to really thoroughly investigate this and think on your own about how this might project forward. So what kind of potentials can you develop with a similar coding structure to this? So this is generally what this kind of output looks like. You can see that it's not doing a great job of following the image in this case. It's slightly starting to steer towards the edges of the image, but in some cases it's actually totally bypassing that. This is because we're using a small search neighborhood. If you wanted to improve this script, and we'll get into it as we go through the video, you would want to have a larger search radius or search neighborhood so that your agents actually have the ability to look further ahead and then make responsive decisions. In general, though, this is going to be combining two previous tutorials. So one, either the structure of a linked instance or a mesh crawler, both similar. So it's going to kind of build on those and then combine it with some of the OpenCV methods. This way we can actually import this image and run these agents. And if I go into a different view, we can see that that's just a visualization. We've just actually imported that picture as a background in Rhino. And that's purely for visualization's sake. It's not actually running on that. It's running on the real image in our file explorer. And then it's constructing trails from the agent path relative to that image in space. In this case, we're just keeping this as a 2D set of trails, but you could have this 3D, you could have this crawling on a mesh, and then still making decisions based on the image, which I recommend doing or looking at after this tutorial and trying to figure that out relative to your project. Okay, so I'm going to just go ahead and delete this, and then I'm going to hide these previews and go back to top view. First, we can just set up our Rhino environment, and then I'll start going through the setup for these components for the OpenCV agent. In Rhino, it will be helpful if you actually save out a view. If you save a view, and ideally it's top view, but this actually does work in perspective or parallel viewports and at any orientation. So it's incredibly flexible as a methodology, but I just want to show you the kind of basic version of it so that you can get comfortable with it. And then if you choose to make adaptations, then feel free to do so. But in this tutorial, we're just going to cover the basics. So if we just click on the Save button in our Named Views tab, or click on the down arrow here, Set View, Named View, and then that would open up this window, which you can then click Save As. This will just allow us to save our current view. So this view we're looking at, which is top view, parallel projection, and this particular scale and extent into our saved view. This allows us to move this around, and then if we ever need to get back to our view that we had snapped, we just double click on that view and it snaps us right back in. This is going to be helpful because we're actually going to be drawing agent seed points inside of the Rhino space. So let's say we have an agent that starts there, or an agent that starts here, or an agent that starts here. We're always going to be controlling those agents with a view to image translation. So if we were to actually move over here, unlike this zoom annotation, which moves with my screen, it would not. But I guess the point is that the agents would be somewhere off the screen and the image would actually follow us. So I guess it's the kind of reverse of what we just saw with these blue annotated agents. But if we just double click back on, then we would always have our image and agent starting points aligned, and we'll always get this preview if we follow tutorial video. So I'm going to just go ahead and clear those, and then we can open up Grasshopper and get started. The most important thing right now is to actually open up this example file, just because it has our GH-Python remote connection up at the top. If you want to, you can disable the actual agent components, but we want to use GH-Python in this case. You could also do this with sockets like we discussed in the previous video, but we're going to just use GH-Python for now so that we can keep it all inside of Grasshopper. Now, if your toggle is set to false, just double click on that to set it to true, and then you should see your terminal pop up. And now we can go ahead and get started. So we can start by double clicking into our canvas, and we can type GH Python script. We can change this name to OpenCV agent. And similar to most other agent setups, we're going to just input here our agent, which in this case is actually going to be a line. To briefly explain this, what we want in this setup is going to be a starting position, so the starting position of our agent. And we are going to need also an initial velocity vector. So let's say we want it to start heading in this direction. So one easy way to have both the starting position and that vector, as well as a magnitude for that vector in the same parameter, is to just say that agent equals this line, and the first position is the starting point of that line, and then we make a vector based on those 2 points, the start and end point of the line. And this way it will start heading in this direction, and in each step it will make a decision of which direction to turn based on certain evaluation criteria, and it will continue to respond to those criteria for however many steps we specify. So that's the base structure. So what we're going to want is an input set of lines. And then here, the X, this is where we're going to have similar inputs to our OpenCV components. So we can say image or I or whatever you want to name that, but this is going to be the reference to our file path. You can now double click, type path, select file path, plug that in, right click, select one existing file, and we can set that path to our reference image file. For lines, we can just make a line parameter. So type line, plug this into lines. We need to, before we set our actual lines, we need to right click on lines and change it from item access to list access. And then we can right click on line, set multiple lines, and hit enter. So we've now set our reference image path. We've set our lines as our initial positions and vectors for our agents. And then before we jump inside, we just want to change this A to a T, as we know that with agents, our output is likely going to be a set of trail curves. So we'll output our trail curves to this T variable. Okay, so to start, we're going to import our libraries as always. So import Rhino script syntax as RS, import script context as SC, import Rhino. So these are our 3 Rhino related libraries. These may actually be redundant, but for now, we're just going to have both of those in there. Then the next thing is to use our GH Python connection to import our modules. So we need numpy, so equals sc.sticky. And we need to grab our numpy module there. Again, we can look at this reference up here. So numpy equals sc.sticky numpy. So we're just labeling it np instead of numpy. And then we have cv2 equals sc.sticky cv2. So those are going to import our numpy library and our OpenCV library. Now, the basic structure is going to be 2 classes, one for our reference image and storing data about our reference image, as well as the context for our agent, and then the second is our agent. So here it is reference image class, and then here we have our agent class. In our reference image class, we can call this class ref image, and all we need to feed this in our init is our self, and then we want to feed it a variable which we're going to pass in our image path. So let's just say I for now, and then we can say self.image equals cv2.imRead, and we are going to read in that I when we pass it in and construct our reference image class. Okay, for now I'm going to leave that class there and call it down at the bottom of the script. So we can call ref image, and we need to feed in our image, so image reference, and let's just set this equal to my image. Now we need to start our agent class, so we can say class agent def underscore underscore init underscore underscore feed in self. And in this case, we are going to need a pause. We are going to need a vec. And for now, that's all we're going to need here, I think. So we can close the parentheses there, hit colon, enter, and we need to convert these into properties of our class. So self.pause equals pause, self.vec equals And in this case, our vec input is actually going to be our line. So we need to convert this to a vector. So we can do this by saying rs.curve endpoint vec minus rs.curve start point of vec. This will give us the vector from the start point to the endpoint and set that equal to our self.vec property. We know that eventually in our agent class, we are going to need a run function. So we can name this run move, feed in self, and for now just pass. So now we need to loop through our list of lines and instantiate class objects of the class agent. So we can say for line in lines, and then we just need to call our agent. So we can say my agent equals agent, and we need to pass in a position and a vector. So our position is going to be rs.curve start point of line. And if we wanted to, we could actually just copy this rs.curve endpoint minus curve start point. We could just copy this into our class instantiation. This way, it just is already a vector when it's fed in. And then instead of vec, we can just feed in line. This is a bit more proper and I think makes more sense overall. And now we just set self.vec equal to vec. And now if we want to run through the run move, we're going to do that for X number of steps. So we would say for I in range, we can go ahead and set this to a variable so that we can adjust this. So for I in range steps, cycle through each of our agents. And in order to do that, we need to somehow append my agent to an overall list so that we can cycle through them. So we would say for agent in, let's call it population. And now we need a list called population. So we can do this at the top, population, and we want to append my agent to population. So population.append. Now for I in range steps, and then for each agent in our population list, we can call the run move function. And we need to refer to the actual instance of that agent, which is going to of that agent class, which is going to be called agent. So agent.runMove. So now the next step is to actually build up our constructor function for our reference image class. So we're bringing in our image reference there, reading it with OpenCV to convert it to a color array. But then there are a couple more things that we need to do here. We want to actually read that image, maybe not as the image itself, but we maybe want to use an OpenCV function, let's say an adaptive threshold or canny edges, something like this. So we are going to need to convert to grayscale. Then let's say call adaptive threshold. So we'll run the method adaptive threshold inside of OpenCV, and we're going to use that as our reference image. So that way it's always reading generally the kind of edges of our reference image based on those adaptive threshold values. Now, we're using this reference image relative to our viewport space inside of Rhino. So in order to actually make this work, we need to make sure that the image size is the same size as our Rhino viewport. So even before we run these OpenCV methods, we actually need to check the size of our Rhino viewport and then adjust that reference image to be the same size. So we can say sc.doc, and we need to first make sure that this is set to rhino.doc.activedoc. And now we can make a variable called self.view and set this equal to sc.doc.views.activeView. And then we are also going to make a property called self.vp, or if you want to use the full name, you can say viewport, and then equals self.view. And then from this active view, we are going to use the active view port. So this will get us the actual view port and not just the view, which gives us the current view name. The actual viewport is going to give us the viewport object. And now we can extract the width and the height. This is going to just be self.viewport.size.width, and then self.viewPort viewport.size.height. Then now that we're done using our Rhino document, we can switch the sc.doc back equal to gh.doc. So sc.doc equals gh.doc here. And we can resize the image. So resize, or let's even just say self.image equals cv2.resize. And if you remember, our resize method is going to take a source image, so self.image, and then dimensions. So dim is going to, we don't have to specify dim, we can just open parentheses and say width, height. And then we just need to specify an interpolation type. So interpolation equals cv2.inter area. Close those parentheses, and we now have our resized image relative to the viewport. Now we can convert this to grayscale, so self.image equals cv2.color. Feed in the source image, self.image, and then our conversion type, which is going to be cv2.color RGB to gray. Now we need self.image, and we're using our adaptive threshold, so cv2.adaptive threshold, which takes a source image, a single color value, so in this case we'll just say white as the background, color value in adaptive type, which we're going to use adaptive underscore thresh underscore Gaussian underscore C, all in caps, and then our threshold type, which is going to be cv2 dot thresh underscore binary. Then we need two more parameters here. So our neighborhood search size, which we can say is 11. And then we need a constant, which is effectively going to be our kind of noise level of this threshold. So we can use 4 and then close those parentheses. We now have our image using the adaptive threshold, and we've saved it as our image property inside of this reference image class. Now, if we want to, we can actually display this. So display adaptive threshold as background image. We can also do this using cv2.imshow or cv2.imwrite. Whatever you would like to use is perfectly fine, but in this case, I just want to see it in the Rhino space so that we know we're actually kind of tracing it properly in the Rhino space. So we are actually going to use a method called, so inside of viewport, if we just go ahead and type this out up here, it will actually show us. So sc.doc.use.activeView.activeViewport, and then this gives us our methods inside of our active viewport. And if we go all the way down to the S's, we should be able to see that there is a set trace image. And if we open parentheses, it will tell us what this takes. So it takes itself, okay, the Rhino viewport, which we're giving it here by calling this method from that class object of the viewport. Then it's going to take a bitmap file name. This is going to be our original file name reference. So feed in I. If we wanted to, we could actually use our adaptive threshold and overwrite this. So maybe we should just say down here, cv2.imwrite, plug in the file path for I, and use the self.image image. And this way, when we use this as a trace, it's going to take our updated image after our adaptive threshold. And okay, now we need a plane, a width, a height, and then these are optional input values. So we're just going to do a plane, width, and height. So we can actually use our viewport information again, so our width and height here. But in this case, we're going to use self.viewport.getFarRect, and we can set rect equal to that. This gives us our viewport projected into space at the kind of farthest depth of our current view. But we're going to just use this as a way of getting the corner points of our viewport and creating a plane from those. If we look at this method, so sc.doc.views.activeViewport.getFarRect, we can see that it returns a left bottom, left top, right top. So the corner points, but it's actually returning each of those points. What we want to do is create a plane starting at the bottom left point. So we're going to say plane equals rs.create plane. And we're going to feed in here our get far rect. Check that again. Left bottom is our first item. So we're going to feed in rect 0. And now we can delete this. And if we check this create plane method again, we can see it takes an input of either a plane or an origin and then an X and Y axis. So we can just feed in that left bottom corner point as our origin, and then we want the X and Y axis as our X and Y axis. So we're going to just say X is 1, 0, 0, and Y is 0, 1, 0. And now we can set plane as an input parameter there, and then we just need a width and a height. And this is not going to be the same as our viewport width and height, as that's our pixel width and height. We want our actual world coordinates for this. So if we check again our get far rect method, we can see that we could actually just subtract one corner point from the opposing corner point. So let's say bottom right from bottom left, or take the distance between those, and we should be able to actually calculate the world space distance of the width and height for this rectangle. So we can say W equals H equals, so W first is going to equal rect of 1 minus rect of 0, or rs dot distance between those two. And then if we copy this for our height, we, instead of 1, which is the bottom right corner, we want the top left distance to the bottom left. So that's going to be index 2. Now we can feed in our width. When we hit test, we should now see our set trace image appear as our background in this view. So it is requiring those booleans. You can just say true for both. And then at the bottom, we just haven't defined our steps. In this case, we can just specify steps here equals 10. Now if we hit test, it should be updating our view, and it looks like it is. So now we have our general setup for the constructor function of our reference image class. Now we want to go ahead and take a look at this run move class. So we're feeding in our self.pos, our self.vec. We can now use these in the run move, but like in other examples with our mesh crawler or even the LinkedIn's ant, we're going to want to add this vector or an updated version of this vector to our self.pos to actually get motion in each of these steps called down here. So the first thing to do, we can just rough that out, and we can say self.pos plus equals self.vec. So this is going to update our position based on that self.vec. Then we can say self.vec equals, and now we need to establish criteria to define this new vector heading. Okay, so the first criteria we're going to program is reading the image, finding a neighborhood of pixel values around our current position. The difficult thing here is we have an agent that exists in the world coordinates of the Rhino interface, but we have an image that exists in a 2D pixel array space. So we actually need to do a bit of transformation there to convert the agent in world space to the pixel space of the image, and then back to the world space to update this. So we're going to do this by calling a function not in the agent class, but actually in our reference image, which is going to be called get image neighbors. And since we want that function to actually be placed as a method inside of our reference image class, and we've called our reference image there my image, we can just say my image.getImageNeighbors. And we don't know what we're going to pass in yet, so for now, let's just leave that and go into our reference image class again. So we can start by making a function, getImageNeighbors. We need to pass in self, and for now, that's all we know. So what we're going to be doing in this function is actually taking a coordinate here with an x, y, z value. We're going to be projecting that into the screen space. So this entire screen space, which will give us an x comma y value, which is an index for one axis of the array and the other axis of the image array. We can then take those index values to actually query the reference image and see whether our reference image has a white pixel or a black pixel. We can also do this to say if it is a white pixel, so let's say we have our current pixel here, this is a black pixel, let's say, we can query all of the pixels around it. So the pixel to the upper left, above it, to the upper right, to the right and left, and then to the lower left, right, and middle. So it's going to query all of this neighborhood of pixel values and find whichever one is closest to the current heading. So let's say the current heading of this agent is up, but the pixel value above that is white, but we have a black pixel to the left here. Then we would select that as our new vector to update the self.vec. So we would then move there, and the agent would trace through wherever our black edge pixel values are. So ideally, this is going to make the agent be able to trace the image based on its edges from the adaptive threshold. So we can just clear that drawing and go ahead and get started with that. So in order to do this translation, we're going to need a point. That point is going to be the position of our agent, so self.pos. And we need to convert that point into a pixel space so that we can check the pixel value at that particular point. So we're going to say image point equals, and we are going to use the viewport method self.viewport. So the viewport inside of this class, self.viewport.world to client, and this is going to take in a point input. Now if we print point and hit test. So we have an error here because we haven't actually created these vectors, but let's just ignore this for now. Hit test. So now we can see all of our positions of each of the agents that we've set here. So these lines, so the starting point of those lines, because we're not actually moving them, but converted into pixel index values. So that's working. Now what we want to do is construct a neighborhood around these. So we can actually just do this manually and create a set. So we can say n0 equals. So I've just written this out already, but basically what we're doing here is saying, take our index value, so print image point, and separate out image point item 1 and image point item 0 and item 1. So our x index value and then our y index value. And in each one of these, we need to add and subtract in each axis separately to get all of the combinations of neighbors around this. So if we just said print image point 0 minus 1, and then print image point 0 plus 1, and then if we hit test, we can now see that it's printing our index, which is 416, 470. And that first item, 416, that second item is 470. 416 minus 1, you get 415, and plus 1, you get 417. So these are our two neighboring index values in that axis. So we then do this for every combination. So minus 1, minus 1, minus 1, nothing, minus 1, plus 1, nothing, minus 1, nothing, plus 1, plus 1, minus 1, plus 1, nothing, plus 1, plus 1. And then we can set our neighbors equal to a list containing n0, n1, n2, n3, and so on. Then we can return these neighbors. So we're going to return that list of our neighboring index values. And if we set image underscore neighbors equal to my image and then print image underscore neighbors, we should get as an output all of our neighbor index values for each step, which we do.